Newton's methods is used to find the root or solution, x-intercept, zero. Of course, those are all synonymous terms, so whatever you want to call it. But it gives us a way that we can find a root or solution or x-intercept or zero of a higher degree equation or transcendental function accurate to 8 or more decimal places. All right, so let's say example number 1. They give me f of x is equal to x to the third minus 2x minus 5 is equal to 0. And they want me to find the root or the solution of that equation. Now, if I were to graph that, this is what that equation looks like. So you can see that x-intercept is pretty close to 2. Sometimes they'll give me a starting value and sometimes they won't. For this particular problem, it says start with x sub 1 is equal to 2. So they did give me a starting value. But if they didn't, you could see I could just look at the graph and go, okay, looks like my x-intercept is pretty close to 2, so maybe I want to be my starting value. You can see how we could get that on our own if we had to. All right, here's what Newton's method says. It says if you know x sub 1, then to find the next successive approximation that's going to get more and more accurate, it's going to get closer and closer and closer to the solution. To find x sub 2, we're going to use this equation. X sub n plus 1 is equal to x sub n minus f of x sub n divided by the derivative of x sub n. So when we want to do x sub 2, okay, we've got x sub 1. If we want to do x sub 2, if I'm putting a 2 right here, if n plus 1 is equal to 2, that means n has to be 1, right? So that would be x sub 1 minus f of x sub 1 divided by the derivative of x sub 1. And so that's what we have right over here. If you want to find x sub 2, it's going to be x sub 1 minus f of x sub 1 divided by the derivative of x sub 1. We were given that x sub 1 is equal to 2. So let's just put 2 in the place of each of those. So 2 in the place of x sub 1, 2 in the place of x sub 1, 2 in the place of x sub 1. So if I did that, it would be x minus my original equation in the numerator and my derivative in the denominator. All right, so my original equation was x to the third minus 2x minus 5. So of course its derivative would be 3x squared minus 2. So here's my setup for Newton's method. X minus the original equation divided by the derivative of that equation. And so to find x sub 2, I'm going to put 2 in the place of each x. Why? Because again, my first starting value, x sub 1, was 2. And so to find x sub 2, it says put x sub 1 in for each of our x's. So we're going to put 2 in for each of our x's. So that's what we're doing right here. We're putting 2 in for each of those x's. All right, so if we plug that in, we're going to end up with 2 cubed is 8, minus 4 is 4, minus 5 is negative 1. And then 2 squared is 4 times 3 is 12, minus 2 is 10. So we'll get 2 minus a negative 1/10, or 2 plus 1/10, so we'll get 2.1. So there's my second approximation, 2.1. All right, then I want to find my third approximation. And to find my third approximation, I'm going to have to go through, if I want this to be 3 right here, what would n be? 2, So that means I'm going to go through and I'm going to plug in x sub 2, x sub 2, x sub 2. X sub 2 was 2.1, so that means I'm going to have to go back to the same equation that we had set up right here. And I'm going to have to put 2.1 in for each x. So that's what we've written here. If you want to find x sub 3, you're going to plug in x sub 2 in the place of each x. And x sub 2 was 2.1, so you'd be putting 2.1 in the place of each x. Now plugging 2 in by hand wasn't so bad. But plugging 2.1 in, not nearly as much fun, because I'm going to have to do 2.1 times 2.1 times 2.1 minus 2 times 2.1 minus 5. I'm definitely going to be using my calculator for that. If I weren't using my calculator on that step, you'll notice that when I plug in 2.1, the answer that I get has like 9 decimal places to it. Yeah, I'm definitely using it for the next one, right? Because I'm surely not sitting here and taking all 9 decimal places and raising that to the third power. But without a graphing calculator, that's exactly what Newton did, right? So amazing, the computations that Newton went through in using this to find these solutions to this type of accuracy. All right, so grab your calculator if you would, and let's look at some efficient ways that we can throw this into our calculator. All right, so to begin with, I'm going to type in my equation. So my equation, okay, so let's type our equation into the calculator. Remember that we're putting in x minus the original divided by the derivative. So our original equation in our numerator will be x cubed minus 2x minus 5. All right, and then down in our denominator, we need the derivative of that, which was the 3x squared minus 2. All right, now, you probably have some random value stored to x on your calculator. Who knows what you have? So when I hit enter and you hit enter, we're not necessarily going to get the same thing, because if you have 10 stored for x and the person beside you has negative 57 stored for x and somebody else has pi stored for x, we're going to get different stuff, okay? But we can tell our calculator what we want x to be, okay? Remember that very first one that we did where we plugged in 2 and we got 2.1? All right, what we could do is we could tell our calculator, take 2 and store it to x. You have a store button on your graphing calculator just like you would on a scientific. It's right above on. It says stow. So when I do that, it says, okay, got it. I got 2 in for x. All right. So now, if you have an 83, you're going to need to hit second enter to get your calculator to retype your equation for you. If you have an 84 with the new operating system, then all you have to do is just scroll up to it and hit enter, and it'll retype that equation down below for you, okay? So if you have an 83, hit second enter, and it'll retype the equation for you. If you don't, if you have an 84, then you can just scroll up to it and hit enter, and it will retype that equation for you. Okay, so we have typed in x minus our original divided by our derivative, because that's the equation for Newton's method. And we've all told it that we want 2 to be x. So now when we hit enter, it's going to put 2 in the place of each of those x values, right? So now we should all be getting the same thing. You're either getting 21 over 10 or 2.1. We should all be getting the same thing. So our calculator just gave us that second approximation. Our calculator just gave us, okay, I plugged in 2 for you and I got 2.1. All right, now I want it to take 2.1 and plug that into the equation, right, to get the third approximation. So all I'm going to do is I'm going to hit that store button again. And when I do, it's going to take that answer that we had of 21 over 10, and it's going to store it to wherever I tell it. So I'm going to tell it x. And so when I hit enter now, it says, okay, got it. Now x is 2.1 instead of 2. All right. If you have a TI-83, hit second enter, and it'll retype the equation for you. Otherwise, you can just scroll back up to that equation and hit enter, and it'll retype it for you. But when I hit enter again, what's it going to plug in for x? 2.1, right. So now it puts in 2.1. That's my third approximation right there. So that's what I would have gotten if I had plugged in the 2.1 by hand. I'm getting my calculator to do it for me. That's my third approximation, right? Now I'm going to store that to x, so I don't have to keep retyping it. Go back and get my equation. And this time when I hit enter, it's going to plug that third approximation in for me and give me my fourth approximation. And I'm going to keep going through this process over and over and over again until I get the same answer twice. When I get the same answer 2 times in a row, then I'll know I'm done. That's as accurate as my calculator can be. Now, be careful, because when I store a value to X, it automatically retypes that value, so it's easy to look at it and go, oh, I got the same answer twice. I didn't. It just was where I stored it to X, okay? So I need to check and make sure, okay, let me store that to X. That's not the same answer twice. That's just my calculator saying, okay, I got that for X. I'll plug that into the equation. And this time, I got the same answer as I did when I plugged it into the equation last time. So when I get the same answer when I plug it into the equation, I could sit here all day long and keep doing this, and it's just going to keep giving me the same answer over and over and over. That is as accurate as it can be. That is going to be my root. Okay? So again, what we did was we wrote our equation to be, according to Newton's method, x sub n plus 1 is x sub n minus f of x sub n divided by the derivative of x sub n. So we said x minus the original divided by the derivative. They will either give me my starting point of 2, or I can look at the graph to get a starting point based on what's closest to my x-intercept. We plugged 2 in by hand, but we could have done it on our calculator, and we got 2.1. Then we asked our calculator to take that 2.1 and put 2.1 in the place of x in that equation, and the next number that it gave me was my next approximation. We stored that to our calculator and said, okay, take that answer and store it to x, and it said, okay, I got it. And then we retyped the equation and said, okay, now plug that into my calculator, and the answer that I get is my next approximation. So that was my fourth approximation. Then I took that and I stored that in my calculator and said, okay, take that and store it, and it says, okay, I got it. And then we said, plug that in, and this time I got the same answer again. That was my fifth approximation. So as soon as you get 2 answers that are the same from plugging them into the equation, not just from where it shows you it stored it, but from plugging it into the equation, then you can stop, because that is your solution. Okay? Now, you are also linking that program called Newton. So let me show you how that program works as well. First, you're going to need to unarchive it when you get it, because it's archived. So to unarchive it, remember you're going to go to second plus sign, which is your memory button. You're going to go to memory management delete, option number 2, and you're going to choose all. And when you scroll down, the program has a star by it. Hit enter, the star goes away, it's unarchived. Anything else you want to archive, just hit enter and the star comes back on and it's archived. But you can archive and unarchive all your stuff all at the same time there. Okay, so if I want to run that Newton's program, all right, I'm going to choose from my programs Newton and hit enter, and it's going to say, what is f of x? That is your original function. That's not the crazy thing where you did the x minus the original divided by the derivative. It's just the original function that we started with. So in this problem, we had started with x to the third minus 2x minus 5, right? Then it's going to ask you for what is your guess? What's your original approximation? If they give you one like they did here, we'll put that in. If not, we'll look at the graph and just see what's a value that's close to that x-intercept. So we could give it the 2. And when we do that, when you hit enter, your calculator is going to like go crazy. Because in essence, what it's doing is it's doing all of this computation that we just did. And if you scroll back up, you'll see we went through several screens on the calculator. So that's what it's doing. It's going through that same process. And when it hits 2 in a row, then the program stops and says, okay, here's your answer. And so sure enough, they're getting the exact same answer that we got when we did it by hand. Okay? So the program will do the same thing for you. Now, you cannot scroll back up through that program to get the list of these values. It won't let you do that. This particular program won't. It'll just give you that last value. Now, I would mention to you that we already know a way of solving equations, finding roots, solutions, x-intercepts as well. That is fast and easy on the calculator. And remember, the way that we would do that is we would go to y equals and type in our equation. So in this case, it was x to the third minus 2x minus 5. And graph it. And I can see, okay, there's a solution right there near 2. So I would go to second trace, which is my calculate menu, and choose my 0 button. And remember, it's always going to prompt me for a left boundary and a right boundary and a guess. So, okay, I would give it a left boundary and a right boundary and a guess, and it's going to give me my 0. Well, yeah, but that's not nearly as accurate because that only has 7 decimal places, and the one that we got on our calculator using Newton's method was 9 decimal places. Okay, well, here's a fun fact about your calculator that you might not know. It doesn't have any more room for any more decimal places there, but it knows more decimal places there. So when it just solved for x, if you'll quit out of your graphing and you'll go back to your main screen and type x and then hit enter, it'll give you the whole x value with all the decimal places that it knows. So that will give me all 9 of those decimal places the exact same way that Newton's was giving it to me. Okay? So it's just kind of nice to have options because yes, I can do Newton's method, or I can work it out using the program Newton, or I can work it out just using my 0 button and I get the same answer every single time, right? Okay, so let's look at another one. For the next one, they ask me to use Newton's method to find the 6th root of 2. Use Newton's method to find the 6th root of 2. Correct to 8 decimal places. All right, so for this one, if I'm going to do Newton's method, I need an equation, right? So I could say, okay, here's the 6th root of 2. Let's set that equal to x. And let's raise both sides to the 6th power to get rid of the radical. And let's move it all over to one side, set equal to 0. So in that way, I've been able to rewrite that radical as an equation so that I can perform Newton's method. All right, so Newton's method is x minus the original divided by the derivative, right? So we're going to have x minus the original, and I would need the derivative of x to the 6th minus 2. So derivative of x to the 6th, of course, is 6x to the 5th, and derivative of negative 2 would be 0. So if we give our setup equation, it's going to be x minus the original divided by the derivative. They do not, for this one, give me an initial approximation or an initial guess or a starting value, but I could figure that out. I mean, I know the 6th root of 1 is 1, so this can't be much more than 1, so 1 might be a good approximation. I also could graph it. If I throw the original equation, the x to the 6th minus 2, if I throw that in y equals and graph it, you can see right here y equals x to the 6th minus 2, then you can see a solution over here really close to 1. So either with common sense or with looking at the graph, I'm going to make my first approximation 1. They didn't give it to me, but that's what I'm going to choose. All right, so then to find my second approximation, we're going to go through and do x minus x to the 6th minus 2 over 6x to the 5th. So let me go grab my calculator and put that in. All right, so we're going to have x minus our original equation, which was x to the 6th minus 2. Divided by the derivative, which was 6x to the 5th. And when I hit enter, I'm going to get some kind of goofiness because remember, it's already got that last value, that 2.09455. It's got that thing stored for x. That's not the value that I want, but I can tell it what I want. So we said our first approximation was going to be 1. So let's tell it 1 store to x, and it says, okay, got it, 1. And then I'll go back up and get my equation. And when I hit enter, it's going to plug 1 in the place of x in that equation. So it's giving me 7/6 or 1 1/6 or 1.16 repeating. Let's store that to x. That's my second approximation right there. So store that to x. It says, okay, I got it. Go back and grab your equation. And this time when you hit enter, it'll plug 7/6 in the place of x. There's your third approximation. Store that to x. Go grab your equation. And there's your next approximation. Not the same thing, so we're going to keep going. So store that to x. Only one x, not two. Go back and get your equation. And we're just going to keep going through this process until we get the same answer twice, which hasn't happened yet. You think this is tedious? Think of poor little Newton doing this with his quill pen and his candle. And admire the genius that is Newton. Still didn't get the same answer, so we'll store that one to x. And plug that one into our equation. There we go. Finally got the same answer 2 times in a row, so I'm done. All right. So again, what we did was we took that 1, and we had our calculator plug it into that equation, and it gave us 7/6 or 1 1/6 or 1.16 repeating. And then we stored that, and it gave us our next approximation. And we stored that, and it gave us our next one. And we stored that, and it gave us our next one. We stored that. And when we got 2 in a row, x sub 6 and x sub 7 are the same, then that was when we knew that we were done. Now, I also could run Newton's program on that. If I run Newton's, it's for the original equation. The original equation is x to the 6th minus 2. So if you go to Newton's and you type in Newton's program, and for f of x, you tell it x to the 6th minus 2, and for your starting value, you tell it 1, it will give you this same thing. I would also remind you that we already have a way on our calculator that we know how to do this, right? If I want the 6th root of 2, I literally can just go to math, and remember that option number 5 down there lets me put in any kind of root that I want. Okay, so I could go through, and I'm first gonna you can either first tell it the 6 for the 6th root and then go grab that button, and ask it for the 6th root of 2, and there's that exact same answer that we just got a second ago. Or you also remember that you could write that exponent as, you could write that radical as an exponent. So if you did that, that would be 2 to the 1/6. And that's going to give you the exact same answer. So we have other ways to do these things that we're learning with Newton's